So we have two minimums and a maximum. If I look at the graph as it's drawn, I get an image that looks like this. And you can see that we do indeed have two minimums when x is equal to negative 2.58 and when x is equal to positive 2.58. And we have a maximum when x is equal to 0. A local max, of course, just a local max. But that's what the question was asking us to find. Now let's see if we can find the inflection points. So I'm going to start off by finding the second derivative, and I'll do that by taking the first derivative again. And then now I'll find the second derivative. I'm going to set it equal to 0. And I've got 30 x to the power of 4 minus 120 x squared. First thing I want to do is simplify this as much as possible. So I'm going to factor out a 30 x squared, and I'm going to be left with x squared minus 4. And I could rewrite this as 30x squared times x minus 2 times x plus 2. Now I'm ready to draw my sine diagram. So I'm going to have 30x squared in the first row of the first column, x minus 2, x plus 2. I think again I've written it just a little too high. I'll bring it down just a little bit. And then I'm ready for my real number line in the top row. And if x is equal to 0, this whole thing is definitely going to be equal to 0. It doesn't matter what those two are. So I can write 0 right here. Oops. Put a line all the way down. And I've got a negative 2 and a 2, positive 2. If x takes on any of these three values, then our second derivative is going to be equal to 0. And this goes all the way down to negative infinity, and this goes all the way off to positive infinity. Now 30x squared, that's pretty easy. Any value of x is going to be positive. A negative squared is positive, so no worries about that one. X minus 2. If x is less than positive 2, it's going to be negative. And x plus 2, if x is less than negative 2, this thing is going to be negative. But if x is greater than negative 2, it's going to be positive. Oh, and I forgot to finish the top one, so I'll add in the pluses there, right? If x is greater than 2, say x were 3, 3 minus 2 is equal to 1, so clearly it's going to be positive for any x greater than negative 2. Now we're ready. If x is less than negative 2, we're going to have a negative times a positive, so this whole thing is going to be positive. And if the second derivative is positive, it's going to be convex. If x is less than 0, but greater than negative 2, it's going to be negative. So it's going to be concave. If x is greater than 0, but less than 2, well, this thing is still going to be negative, so it's concave. And if x is greater than 2, it's going to be positive, and so it's going to be convex. So we can summarize here, and we can say that x equals -2. Well, it's going from convex to concave, so it must be an inflection point. Remember, any inflection point occurs when we're going from convex to concave or concave to convex. And so x equals 2 is also an inflection point. I forgot my point in the first one. I'll write that in. What about x equals 0? Well, it's going from concave to concave, so is not an inflection point. It's not an inflection point. Let's take a look at the graph. Remember, it was a local max. So we can't, a point can't be both a local max and an inflection point. A point can't be both a local minimum and an inflection point. We can draw on this graph right about there. Right about there. Here are our inflection points. Another inflection point, and not an inflection point. And that's how we find inflection points. It's a little bit of work, but if you stick with the algorithm and you develop some intuition, think about what you're doing, think about what your results mean, I hope it makes a lot of sense to you and it's not too complicated. Here is the textbook definition of an inflection point. Remember that if we're interested in some candidate point C, it is a necessary condition that the second derivative be equal to 0. So if the second derivative is not equal to 0, it is definitely not an inflection point. Right? So f w c greater than 0, c is not an inflection point. Right? That's essentially what 1 is saying. It's a necessary condition that the second derivative must be equal to 0. And this is what's kind of giving us the algorithm we followed for finding inflection points. Right? We use the Sine diagram to show that the function was going from being concave to being convex, and therefore, when the second derivative was equal to 0, it was actually an inflection point. So this is just a necessary condition, not a sufficient condition. And this is, gives us the recipe for going out and finding whether a point is an inflection point. Here's an example for you. See if you can find all the local extrema and inflection points given this function. Press pause on your video, work through it yourself, and when you're ready, I'll walk through a solution with you. All right, let's work through this example together. First, let's find the local extrema. So I want to take the first derivative, and the first derivative is going to give me negative x to the power of 3 plus 48x, and that's going to be equal to 0. Then I want to do my best to factor this thing out, and I can do that by factoring out a negative x. I think I'll factor out a negative x, and that will give me this value equal to 0. Now clearly this whole thing's going to be equal to 0 if x is equal to 0, but it'll also be equal to 0 if x squared minus 48 is equal to 0. And that's going to give me x plus minus the square root of 48. We'll say that that's approximately 6.9, 3. Plus or minus. Negative, positive, or negative. Now I'm ready for my sine diagram, and so I'm going to do it like this. I'm going to have a negative 1 on x, and then x squared minus 48. I'm going to separate my x and my negative just to make it a little less confusing for me. Now I've got my real number line here. I know that 0 is an important number, negative 6.93, and positive 6.93. These are the things that I want to evaluate. Negative 1 is always negative. X less than 0, well, that's going to be negative for sure. And then positive if it's above 0. What about x squared minus 48? Well, if x is less than 6.93, say it was negative 8, well, negative 8 is going to make this thing here positive. So it's going to be positive. Then if we've got a smaller number, like say negative 5, this whole term, the whole thing, is going to be negative. And it's going to stay negative unless x is greater than 6.93, in which case it's going to be positive. And so if x is less than negative 6.93, the first derivative is going to be negative, so it's decreasing. Oh, that's totally wrong, right? We've got a negative times a negative times a positive, so it's actually going to be positive. And f prime of x is increasing. Then if x is greater than negative 6.93, we've got a negative value. Negative times a negative times a negative. It's going to be going down, so we know we've got a max, right? This is the top of the hill. It's the top of the hill. When we get to 0 and we go above 0, we've got a negative times a positive. Positive. It's going to be increasing. And then we've got a negative over here. It's going to be decreasing. And so we've got a minimum here, and we've got a maximum over here. And we can see that because it's going down and then up. So you're in the bottom of a valley, and then over here it's going up, and then it's going down. So you're at the top of a hill. Now, what about those inflection points? So we want to find the second derivative. First, I'll take the first derivative. Got negative x cubed plus 48x. And then now I want to take the derivative again to find the second derivative. I'm going to set it equal to 0. Got negative 3x squared plus 48. And I want to simplify this as much as possible. So I'll factor out a 3, negative 3. So I'll write negative 3 like that. Now I've got x squared minus 16. What values of x are going to make this expression equal to 0? Give us a second derivative equal to 0? Well, we've got, we need this thing to be equal to 0. So we get x squared minus 16 is equal to 0. We get x squared is equal to 16. And then x is going to be equal to plus or minus 4. Well, yeah, it's 4. The square root of 16 is 4. Now I'll move this up. Ready to draw the sine diagram. I've got negative 3 and x squared minus 16. And I'm going to draw the real number line up here. What are my values of interest here? My values of interest here are negative 4 and positive 4. Not really interested in 0, because when x is equal to 0 in this case, we get an actual number, right? So not really interested in 0. Negative 3, wow, that's a negative for sure. Now, x squared, if we've got a value less than negative 4, say negative 5, this is going to be positive. Then if we've got, say, negative 3 in there, the whole expression is going to be negative. And if we've got, say, a positive value in there like 5 squared minus 16, that's going to be positive. So we've got positive out here on the right. And then I want to know the sine of a second derivative, and I get a negative, so it's concave here. It's positive here, so it's convex. And then it's negative over here, and so it's concave. So it's concave. And so we've got an inflection point here. And another inflection point over here. Here's the diagram. So we've got we've got a max. We've got a max. We've got a min. And we've got 2 inflection points. That tell us when the function turns from concave over here, concave to convex. Right, it's concave over here, and it's concave up there, and then down here it's convex. So those inflection points tell us when the function is changing from concave to convex and from convex to concave.